These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Okay, so to start with, see if you can find a way to re-express this expression.
Okay. Okay.
Excellent. So this is something we talked about before, how to add fractions. In order to add fractions, you need a common denominator. Well, we already had a common denominator here. So you just add the two numerators and you keep the denominator the same. Some people have trouble with that when there's variables instead of numbers, but you did that correctly. So what's the advantage of what we did here? Well, we started with two fractions and we ended up with one fraction. Sometimes it's better to have two fractions. Sometimes it's better to have one fraction than two. On the other hand, sometimes it's better to have two fractions than one, but in any case, we need to know that this is one way we could re-express that. That was good. I'll go back to my screen.
Okay.
Try to find a way to re-express this expression.
Okay. Okay.
Okay, how can you check that you did that correctly?
You can add them together and see if you got this answer. They're starting.
Good. Does that work?
Yep.
Yes. Okay, good. So in this case, we started with one fraction, and it seems like we regressed because we ended up with three fractions. Well, it turns out sometimes that is helpful. Sometimes it's helpful because now we have, even though we have three fractions, all of them are simpler than the one we started with. So you can see from these two examples, sometimes it's helpful to take multiple fractions and combine them into one. But what people often forget they can do is that you can also take a single fraction and split it up into multiple fractions. Sometimes that can be helpful because the fractions could end up simpler than the ones that you started with. Very good. I'll go back to my screen.
Okay.
So what you did was exactly what I was going for there. That was a good answer. But I would point out that we've also seen a different way to deal with this. It's not going to be too important today, but remember the other way that we've seen to deal with this is like this.
Mm-hmm.
This would be an alternative. This would be the advantage of this. The advantage of this approach is it gets rid of kind of almost all the fractions. The disadvantage is that it puts in some parentheses. So this is the method that we used in the optimization section. So I felt that was worth reminding ourselves of. But on the other hand, I'm going to erase that now because the method that you used actually will be more helpful in this section. So that's the challenging thing about algebra is that there's more than one path you can take, and you have to use judgment and experience to decide what the best path is. But the way you wrote it out here really will be most helpful in this section. Okay, very good. So we've seen that you can take a single fraction and split it up into multiple fractions. So that's the review of the algebra that we'll need today. Try re-expressing this.
Okay. Okay.
Okay, excellent. I'll go back to my screen. So your thought process was good. The derivative of a constant is 0. We actually spent some time explaining why it makes sense that the derivative of a constant has to be 0, but we won't review that now. We'll just memorize that. Okay. Well, maybe rather than going back and forth between our screens, maybe these problems will be simple enough that you can just do them aloud. So how would you re-express this?
1. Yep.
Okay. Any particular reason or rationale that got you to that?
Because, oh, it's a constant. Okay, well, yeah, if it's a constant, it's 0. I was thinking it was a variable, like x.
Okay. So what's the answer?
0.
Using the constant rule. So it sounds like you were trying, at first you were using the power rule. But as we've discussed previously, the power rule doesn't work when the base is constant. Okay. So this, in fact, what made you got this one right, so why did we get this one wrong originally? Well, the problem is that most people have a bad habit of assuming that all letters stand for variables, but letters could also stand for constants. Okay. What would this be?
0.
Because it's a constant. Okay, good. What would this be?
1.
That's right. How do you know this is a variable? Well, first of all, remember that if you're not told otherwise, we usually assume that letters from the end of the alphabet are variables. And plus, x, we just almost always use x for a variable. So it's reasonable to assume that this is a variable. Good. How about this?
Let's see. That would just be -6.
Good.
That would just be, let's see, 1/5 x. That would be 5. X to the 4th.
Like this?
Yep.
How did you get that?
We can use the power rule, and that would give us 5/5x to the 4th, and 5/5 is just 1.
Excellent. Very good.
Yep.
So here you're using the power rule. You were pretty much using the power rules up here too. If you just remember that the exponent is a 1, you could apply the power rules in those cases as well. Okay, good. How about this?
That's 1/x.
Excellent. Now, do you remember we did an exercise previously where we graphed the natural log of x to see what its domain is? Do you remember what the domain is of natural log of x?
All positive numbers.
So can you plug 0 in?
I don't think so.
Can you plug negative numbers in?
No.
Okay, good. That's good that you remembered that. You can always check that by drawing a graph, and you'll see the graph only exists for positive x's. However, there's something we can do here to use negative x's. You could think about this function. Would you agree that now it's okay to plug in negative x's?
Yep.
Because the absolute value sign will make them positive, and then the natural log will be cool with that. So this is a function you can use. It turns out, this isn't really obvious, this isn't obvious, but we'll just memorize it. Turns out that the derivative of this function is also 1/x. Okay. So that's not obvious, but we'll just memorize that as a new fact. It turns out that the derivative of this function is also 1/x. This would be defined for all x's except 0. This function, you still can't plug in 0. 0 still won't work, but this would be defined for all x's except for 0, because all other x's would be converted into positive numbers, and then you could take the log of them. Okay, so that's a new fact that we didn't talk about before. Cool. Mildly cool. What would this be?
Let's see. This is just 1/x.
All right, that's just what we were just reviewing. Very good. Okay. How about this?
Derivative of cosine of x is negative sine of x.
All right, it's good that you remembered the negative sign there. We hadn't talked about that for a while.
This is just cosine of x.
Cosine x or negative cosine x?
Just cosine x.
Okay, good. I tried to bully you out of your answer, but you stuck to your guns. Excellent. So you got to be confident about what the signs are, and you got that exactly right. So we just have to have that pattern of signs memorized. That's good. How about this?
This is 3e to the x.
That's right. This is a very unusual function. We've seen that natural exponential functions are their own derivative. That doesn't work for other functions. So what type of function is its own derivative?
E to the x?
Yeah. Are other functions their own derivative?
No.
No, just e to the x or a constant times e to the x. Okay. Okay, so I think now we reviewed some algebra that we needed for today, and now I think we reviewed some of the previous calculus that we needed for today. So let's see. What could we say here? Yeah, so what would this be?
Okay. This would be 8x to the third.
Okay, now how would we describe this? How would you read this equation aloud?
The derivative of 2x to the fourth is equal to 8x cubed.
Excellent, very good. That's review. Now we're going to see a new way to express this. Another way to express this is like so. So now we're going to introduce a new concept, the concept of antiderivative. And I guess the easiest way to understand what an antiderivative is just to look at a couple of examples. So here, can you see why it might be logical to say the antiderivative of 8x cubed is 2x to the fourth?
Yep.
So antiderivative is, I think, easier to define with examples than with words. How would you define an antiderivative in words? Well, the antiderivative of 8x cubed is the function that if you took its derivative, you would get 8x cubed. It's kind of a long sentence. The antiderivative of 8x cubed is the function that if you took its derivative, you would get 8x cubed. So it's a little hard to put it into words, but I think if you look at a couple examples, we can get the idea of what an antiderivative is. Notice that taking the antiderivative undoes taking the derivative. If you start with 2x to the fourth and you take its derivative, what would you get? If you start with 2x to the fourth and you take its derivative, what would you get?
You get 8x cubed.
And then if you took the antiderivative of 8x cubed, what would you get?
2x to the fourth.
It would take you back to where you started. So the antiderivative is kind of the inverse or the opposite of a derivative. It undoes it. It's just like, how could you undo addition with subtraction? If you add 3, you can undo it by subtracting 3. How can you undo multiplication? With division. If you multiply by 2, you can undo that by dividing by 2. How can you undo squaring something? Well, you can undo it by taking the square root. If you square something, you can undo it by taking the square root. So we've seen many times that you can undo, in math, there's usually an inverse way to undo an operation. So the way to undo derivatives is to take the antiderivative. Okay, good. So what's this?
6x.
How would you express that in words?
The derivative of 3x squared is 6x.
And how else could we express that in words?
The antiderivative of 6x is 3x squared.
Say that again.
The antiderivative of 6x is 3x squared.
That's right. I think you said it right, but I got confused. Okay. Excellent. Okay. Very good. Okay. How would we how would we write this?
Okay, that's 6x.
Like so?
Yep.
That's right, because the derivative of a constant is 0.
Mm-hmm.
So how would you express this in words?
The derivative of 3x squared plus 8 is 6x.
Excellent. And how else?
The antiderivative of 6x is 3x squared plus 8.
So if you compare these two cases, what we can see is a function can have more than one antiderivative, right? The moral here is, what is the antiderivative of 6x? Well, it's kind of an unclear question because so far we've listed two antiderivatives. 3x squared is an antiderivative of 6x, but 3x squared plus 8 is also an antiderivative of 6x. This is where it starts to be different, maybe from the other things I talked about. Subtraction only gives you one answer. Division only gives you one answer. But taking the antiderivative can give you multiple answers. So would you agree there's only one derivative, but there's more than one antiderivative?
Yep.
3x squared only has one derivative, but 6x has more than one antiderivative. What's this?
6x.
So how would you express this in words?
The derivative of 3x squared minus 5 is 6x.
Good. That's the only derivative it has. How else would you express that, though?
You could also say that the antiderivative of 6x is 3x squared minus 5. And then, yeah, that's it.
Good. Well, now we've listed three antiderivatives of 6x. 3x squared is an antiderivative of 6x, 3x squared plus 8 is an antiderivative of 6x, and 3x squared minus 5 is an antiderivative of 6x. So really, we shouldn't be saying the. We should be saying a antiderivative, right?
Okay.
It's not true that because the indicates there's only one. One of the or maybe we should say one of. I don't feel like writing that out, but we could say one of the antiderivatives of 6x is 3x squared. Another antiderivative of 6x is 3x squared plus 8. And another antiderivative of 6x is 3x squared minus 5. So you could call each of these particular antiderivatives. One particular antiderivative of 6x is 3x squared. Another particular antiderivative of 6x is 3x squared plus 8. Another particular antiderivative of 6x is 3x squared minus 5. How could we write the most general antiderivative? Well, let's do this. What would this derivative be?
6x.
Good. So how would you read that in words? Because the derivative of a constant is 0. Good.
Okay, so the derivative of 3x squared plus 8 is 6x.
Good.
And the antiderivative of 6x is 3x squared plus 8.
Now maybe we can use the word the, because this covers all the possibilities. All the antiderivatives of 6x would fit this expression. All the antiderivatives would fit this expression. For example, this matches the expression. In this case, we just set c equal to 0, right? In this case, c was 0. And in this case, c was 8. And in this case, c was negative 5. Notice it's possible for c to be negative, even though we're adding it. It could still be negative. So this is what we could call the most general antiderivative. This is the most general antiderivative of 6x. It's 3x squared plus c. Okay, good. All right, so those are some important ideas. What would this be?
15x squared.
So what's the relationship between f prime and f?
F prime is the derivative of f.
Excellent. But what's another way we could express that now?
We could say that f of x is the antiderivative of f prime of x.
Excellent. So there's a new way to see the relationship between these. F is the antiderivative of f prime. Now in this particular case, I guess we should say f is a particular antiderivative of f prime. Not the most general, but in this case f is a particular antiderivative of f prime. Okay, so that's an important distinction between those. Okay, so here's a problem.
Right.
If f prime of x is 8, what is f of x?
Right. It would have to be 8x.
How can you check that?
You can take the derivative of 8x and see if you get the f prime from above.
Right, so what's the derivative of 8x?
Just 8.
So did it work?
Yep.
Excellent, excellent. Except that was a great answer, but if this was a test question, we would not get full credit unless we did this. Because the test is going to want us to express the most general antiderivative.
Okay.
So this is one thing that's easy to start forgetting here. We have to get into this habit of always adding this constant here. Because what's the derivative of 8x plus c?
Just 8.
Also 8. So by the way, what are we going to treat c as? A constant or a variable?
A constant.
Yes, c will always be a constant in this chapter. C will always be a constant in this chapter. Okay, so if this was a test question, this would be the answer that they were going for here. So notice, what was the skill that you just used here? You took an antiderivative. Even though the problem never mentioned the word antiderivative, that was the skill you needed. You needed the skill of taking an antiderivative. How do you take antiderivatives? Well, in a way, you do it by trial and error. If you weren't sure what the answer was here, you could have just taken a guess, and then just keep checking your guesses until you get something that works. So you can take antiderivatives by trial and error and checking your guesses. But obviously, once you start to see the patterns, your guesses will get much better and you'll start to get to the answer more quickly. Okay, good. This is a 6.
Okay.
Let's do this problem.
Okay, so f prime of x equals 6. So f of x equals 6x plus c.
Excellent. How would you check that?
You take the derivative of 6x plus c and you should get 6, and that's true.
Very good. Perfect. All right, let's try this.
F prime of x is negative 2. So f of x equals negative 2x plus c.
Like this?
Yep.
Okay, excellent. Yeah. So I threw in a negative sign there, but that didn't mess us up. Good. Let's try this one.
F prime of x is 1. So f of x is x plus c.
Like this?
Yep.
Yeah. What's the derivative of x plus c?
Just 1.
That's right. So that works. Excellent.
F prime of x is negative 1. So f of x equals a negative x plus c.
Good. Okay, very good. So that's some good progress there. Now, remember f prime is the derivative of f.
Mm-hmm.
What is the, so here we said f prime of x was 6. What is the graphical interpretation of the derivative? This is something we've talked about in the past. What's the graphical interpretation of the derivative?
As x increases by 1, then the function f increases by 6.
In general, it would increase by approximately 6. But in this case, because the derivative is a constant, it would increase by exactly 6. Okay, good. That's a correct interpretation. That's good. What I was going for there, though, was another interpretation that we called the graphical interpretation. What's the graphical interpretation of the derivative?
Okay, so if f prime of x equals 6, the derivative equals 6, so the slope of the tangent line to the function f is going to be positive, so it's going to be upwards and fairly steep.
What will be the slope of that tangent line?
6.
Okay, that's right. So the graphical interpretation of the derivative is it tells you the slope of the tangent line to the function. The graphical interpretation of the derivative is it tells you the slope of the tangent line to the function. Now, this is a kind of a weird derivative because the derivative is constant. Most derivatives are not constant. Most derivatives are like this, right? Most derivatives are like this. They're not constants. They're functions of a variable. This is a weird derivative because it's a constant. What does it mean? So this means that the slope of the tangent line is the same everywhere. So what does the actual function look like when its derivative is a constant?
Right. It's going to be a horizontal, it's going to be a horizontal line.
Like this?
Yep.
What's the slope of a horizontal line?
0.
Not 6.
Right. That's not right then.
So it can't be horizontal.
Okay, so...
But the key is it'll be a line.
Straight line.
Will it be upward or downward sloping in this case?
Upward.
So the point here is you already told me that in this case the tangent line would be upward sloping with a slope of 6. But if the slope is the same everywhere, then the function itself is a line.
Okay.
In fact, the function is this line, right?
Right.
Do you remember the y equals mx plus b equation?
Mm-hmm.
So according to y equals mx plus b, what's the slope of this line?
6.
Which we already knew from the derivative. So I'm just trying to point out how this makes good sense if you plug it into y equals mx plus b. If the derivative is a constant, we already should have known that that means the function is a straight line with a slope of 6. And that's what we got. The function is a straight line with a slope of 6. But there's many straight lines it could be, right? There's many straight lines with a slope of 6. They all have different y-intercepts. That's why c could be different for all of those. Okay, good. So for example, what does this mean? This means that the function is a straight line with a slope of -2. Well, that's what we got here, right? What's the slope of this line?
It's -2.
That's right. Here we have a straight line with a slope of 1. Okay, so I just wanted to point out that these answers we've been getting match well with the y equals mx plus b formula. Okay. So what does it mean when the derivative is a constant? What does that tell you about the function when the derivative is a constant?
The function is a straight line.
That's right. Does it have to be horizontal?
It could be, but no.
Yeah, it doesn't have to be horizontal. Good. Suppose that the derivative was 0 everywhere.
Right.
What would that tell you about the line?
We'd have a horizontal straight line.
Yeah.
Well, I guess horizontal is straight. Okay.
Okay. So what we're going to do now here is we can start to make a kind of a table. So if the function is k, what would be the antiderivative?
The function's k. The antiderivative would be kx.
Excellent. Now, the general antiderivative would be kx plus c. But in this table, it'll be more helpful just to focus on a simple particular antiderivative. So one particular antiderivative here would be kx. So this is the first line of our table. Remember I said that the way to find antiderivatives is by trial and error. But if you memorize this line of the table, you won't need trial and error for constants. You'll just know how to take the antiderivative. Okay? Because what's the derivative of k times x?
Derivative of k times x is just k.
Good. By the way, what's the difference between k and x?
K is a constant and x is a variable.
Absolutely. So even though they look similar, they're playing entirely different roles here in that table. That's very important. All right, this one's harder.
Okay. So if f prime of x equals x squared, then f of x must be, so the antiderivative of x squared would be 1/3 x cubed.
Like this?
Yeah.
How would you check that?
You could take the derivative of 1/3 x cubed, and you should get x squared.
Yeah, what is the derivative of 1/3 x cubed?
Let's see. Well, I guess that's wrong. Wait, it would be 1/3. Wait. Yeah, it would be 1/3 x squared. No, sorry. It's x squared. Yeah, that's right.
So what's the derivative of 1/3 x cubed?
X squared.
So is this answer correct?
Yep.
Okay. This one I almost succeeded in bullying you out of it, but you eventually you decided that that is the correct derivative. Okay, that's right. Because this derivative would be 1/3 times 3x squared, which is x squared. Good. Mm-hmm. Okay, excellent. So that's correct. But it's always good to double check, especially at the beginning, to make sure that we're getting these correct. Okay, that was harder than the earlier one, so that's good that you got that right. Now, if this was a test question, though, we'd have to say this. Okay, so that's something we have to get in the habit of doing. But anyway, that's really good that you came up with this correct answer here. What would you have done if your first answer wasn't right? Well, you could just try trial and error. You hopefully just keep taking guesses until you get something that works. Hopefully, if you use good judgment, it wouldn't take that many guesses to get something that works. Okay, very good. So that's good that we came up with that. That's a very important antiderivative. Let's try this.
Okay, so f prime of x equals x cubed. So f of x, the antiderivative is, let's see, 1/4 x to the 4th plus c.
What's the derivative of 1/4 x to the 4th plus c?
Let me double check. Okay, x cubed.
So is this right?
Yeah.
Okay, outstanding. Excellent. Very good. All right, now we could speed up this process if we could see a pattern in these two examples. What's the pattern here for taking the antiderivative? What do we do mechanically to take the antiderivative?
Right. We can use, instead of the n minus 1 rule, we use the n plus 1 rule. So we just take whatever the f prime says. So it says x squared up top. So we could take 2 plus 1, which is 3, and put it over 3. And if the leading coefficient is just 1, then it's 1/3 x cubed.
Okay, good. So let's try to streamline that, but that's good. So what are we doing? We're increasing the exponent by 1 and putting 1 over that new exponent in the front. That's kind of the way to put it in words. We're increasing the exponent by 1 and putting 1 over that exponent in the front. So notice these two numbers match. These two numbers match. If you just keep that in mind, then it should be pretty easy to come up with the right answer. So increase the exponent by 1, and then put 1 over the same number that you just wrote in the exponent. How do you take the antiderivative? So what we're doing here is finding how to take the antiderivative of a power function, right? Mm-hmm. So what we're basically going over here is the power rule for antiderivatives. The power rule for antiderivatives. The power rule for antiderivatives is increase the exponent by 1, and then the coefficient is 1 over the new exponent. The power rule for antiderivatives is increase the exponent by 1, and then the new coefficient is 1 over the new exponent. Okay. And if we have that memorized, then we don't need trial and error anymore, even though it's still good to double check our answers. It's a 6.
Okay.
So let's try this.
Okay. So f prime of x equals x to the 6. So f of x, the antiderivative is, let's see, 1/7 x to the 7th.
We're using the power rule for antiderivatives. So the mechanical process is increase the exponent by 1, and the coefficient is 1 divided by the new exponent. Excellent. Mm-hmm. So what's the answer?
1/7 x to the 7th plus c.
Very important. Okay. So it looks like maybe we're about to leave that out. Okay. Yeah. So it just takes a little practice. Good.
Okay. So this would be 1/12 times x raised to the 12th power plus c.
So that's the power rule for antiderivatives. We raised the exponent by 1, and the new coefficient was 1 over the exponent. Excellent. That's a 4.
Okay. Okay, so this is the antiderivative of f prime of x is going to be 1/5 times x raised to the 5th plus c.
Okay, very good. All right. So again, we're using what's called the power rule for antiderivatives because this is a power function. Now, when does this apply then? When does this apply? It only applies, remember, what's the definition of a power function?
It's a variable raised to a constant.
So this whole apparatus only works if the base is a variable and the exponent is a constant. Could we use the power rule for antiderivatives to find the antiderivative of this function?
No.
Because it's not a power function.
Right.
It's an exponential function. So we'll need some whole new technique for this. We don't know how to do this one yet. By the way, again, this also only works when the base is a single variable. So could we use this approach to figure out the antiderivative? Could we use this approach to find out the antiderivative of this function?
Not yet, no.
No, because the base is not a single variable. We'll need some advanced techniques for that. So this only works for power functions where the base is a single variable all by itself. That's not similar to some patterns we saw for the derivative. What's the most common mistake that I see people make here? Here's the most common mistake. The most common mistake I see people make here is they do this. And they say this is the answer. Can you see how this could be tempting?
Yeah, it's just the derivative of the derivative. So
yeah, it's just a derivative. Why is that tempting? Because what have you been doing for months now in the course? You've been taking derivatives, right? All along in the course, you've been taking derivatives. So your brain has this mental habit now. Whenever it sees an exponent, it wants to bring the exponent down and reduce it by 1, even when it's not appropriate. Your brain is going to want to take down the exponent and reduce it by 1, even though that's not appropriate in this situation. So I'll just warn you against that right now. What you're used to doing is taking derivatives, but you need to fight against that right now. You need to remember that a lot of the time now we're not taking the derivative, we're taking the antiderivative. When you take the derivative, what happens to the exponent?
It comes down and you reduce it by 1.
You reduce it by 1. But when you take the antiderivative, what happens to the exponent?
You add 1.
You add 1. So it's important not to confuse those two. Okay. So I think we're ready now to add this to our list. Let's see. So how could we summarize the types of functions that we've been talking about here? We could summarize that like this. What does x stand for here?
A variable.
And n?
A constant.
That's right. Maybe I'll make a note that n is a constant here. Do we have to use x for the base? Well, no. We have to use a variable for the base, but it doesn't have to be x. That's just the letter we happen to use here. And so what should I write down as the particular antiderivative here?
Okay, we can write down x raised to n plus 1 over n plus 1.
That's right. Very good. That's correct. Now, that doesn't quite match the way we've been writing these. The way we've been writing these
Okay.
has been like this. Now, you might have said it that way because that's kind of the way the table that your instructor gave you looked. And that's fine. I think this is, in the long term, going to be a better way to write it, though.
Okay.
Would you agree that this is the same as this?
Yep.
Yeah, how could you prove that this equals this?
You could distribute the 1 over n plus 1, and you get what you wrote below.
Good. It wouldn't exactly be distribution, though. It would just be multiplying two fractions. If you multiply the two fractions, you would get this. Distribution occurs when there's an addition inside of the parenthesis. Okay? Okay, so that's another particular antiderivative. Raise the exponent by 1, and then the coefficient is 1 divided by that exponent. All right, you might already know how to do this or be able to figure it out, but to save time, I'll just demonstrate what I think is a good way to attack this problem.
Okay.
So notice here we have a power function times a constant. Well, it turns out there's a trick. The trick is just pull the constant out of the antiderivative, so to speak, and just take the antiderivative of the power function. What's the antiderivative of x squared?
1/3 x cubed.
Excellent. And of course, then we'll add this. All right, and now we're done. That's the answer. So that's the trick you can use when there's a constant multiplied by a function. That's the trick when there's a constant multiplied by a function. Do you remember when we were doing derivatives, we talked about something that was called the constant multiple rule for derivatives? We didn't talk about it too much, but sometimes we talked about a constant multiple rule for derivatives. We said that when there's a constant multiplied by a function, you can take the derivative by just taking the derivative of the function and multiplying it by the constant. Well, it's pretty similar here. When there's a constant multiplied times another function, just take the constant out and multiply it by the antiderivative of the function. It's a little hard to put into words, but if you see an example, you can see how it works.
Mm-hmm.
So that's the constant multiple rule for antiderivatives. All right, so here's another problem. Do you have that one written down?
Yep.
All right, let's go through that one together again. So again here, we don't just have a simple power function, we have a constant times a power function. So I'm going to use the constant multiple rule. I just pull the constant down, and now I'm just going to take the antiderivative of x to the fourth. So what's that?
1/5 x to the fifth plus c.
Good, and then we'll rewrite that. What's 7 times 1/5?
7/5 x to the fifth plus c.
Good. And what's 5 times 1/3?
5/3.
So that's how we could rewrite this. Okay, so those are some examples of how to use the constant multiple rule. Now, in this particular case, we had a constant times a power function, but the constant multiple rule would work in any situation with a constant times a function. This doesn't have to be a power function to apply this approach. You just pull the constant down and take the antiderivative of what it was getting multiplied by. All right, so there's a formal definition of the constant multiple rule in your textbook, but I think it's more useful for us just to kind of demonstrate it with those examples. All right. Okay, so now it's your turn. Let's try this example.
Okay. This would be 1/2 x to the 4th plus c.
Okay, like this?
Yep.
All right, now check that.
Okay. The derivative of 1/2 x to the 4th. So 4 times 1/2 is 2. 2x cubed plus 0. Yep, that's right.
Okay, excellent, good. All right, good. I thought you made a mistake there, but actually you just did hadn't mentioned some of the steps there. Excellent. So the process for doing this would be 2 times 1/4 x to the 4th, and then 2 times 1/4 is 1/2. So you did end up with the right answer. Excellent. Okay, good. Okay, let's try this example.
Okay. So f prime of x equals -3/6x. So we can write the antiderivative as -3 times 1/7 to the 7th plus c. And then we can rewrite that as -3/7 x raised to the 7th plus c.
Outstanding. Excellent. So that's the exact right approach. Very good. So I threw in a negative sign there, but you handled that correctly. Let's try this one.
Okay. So -x to the 4th. The antiderivative of -x to the 4th would just be -1 times 1/5 x to the 5th plus c. So it's just -1/5 x to the 5th plus c.
Like this?
Yep.
Okay, check that.
Okay. So 5 times 1/5 is 1, and -1 minus -x to the 4th. Yep.
Okay, very good. Excellent. All right, so again, I was trying to confuse you with the negative sign here, but you handled that correctly. One thing that you did that was good here, it sounded like you explicitly said to yourself, -x to the 4th really means -1 times x to the 4th. And the advantage of that is now you can use the constant multiple rule. And then you pulled out the -1 here. It sounded like you were kind of thinking of it that way because you said there was a -1 here. Okay, good. Okay, I think we got that constant multiple rule down. So next... All right, tell me when you have that one written down.
Yep.
Okay. All right. Well, I'll demonstrate what I think is the best approach here. So the key thing here is now we have a sum of functions. Well, remember there was a sum rule for derivatives. There's also a sum rule for antiderivatives. And basically what it tells you is, remember that derivatives work nicely for addition, right? You can basically kind of do what feels natural when you're working with derivatives and addition. And as a result of that, antiderivatives also work well for addition. So remember that this what we said was the derivative of a sum is the sum of the derivatives. Well, it turns out that the antiderivative of a sum is the sum of the antiderivatives. That's the sum rule for antiderivatives. The antiderivative of a sum is the sum of the antiderivatives. So all we have to do here is just take each of the 3 antiderivatives separately and then just add them up. So what's the antiderivative of 4?
4x.
Excellent. And what's the antiderivative? And then we'll add the next. What's the antiderivative of 3x to the 6th?
Okay. That would be 3/7 x to the 7th.
Excellent. Good. You could check that. Good. And then what's the derivative of negative 4x to the fifth?
4 6x to the 6
So what should I write here?
minus 4 6 x to the 6, and then plus c.
Excellent. That's good that you remembered the plus c. Okay, very good. So notice there's also a difference rule for antiderivatives. Here we're subtracting, so we bring down the subtraction sign. Excellent. And there's one little simplification I can make here.
We can rewrite this as 4x plus 3/7 x to the 7th minus 2/3 x to the 6th plus c.
Excellent. We might as well reduce that fraction to 2/3. Okay, so that's the sum rule for antiderivatives. It's pretty straightforward to apply. Very good. Let's try this on your screen.
Okay. Okay, so okay.
Let's check that.
Okay, so let's see. The derivative of 1/2 x to the 4th is 4/2, 2x cubed. Derivative of 7x is just 7. Derivative of 8/5, so 40/5, which is 8. Okay, cool. Yeah, I think it's good.
Okay, very good. Great. Okay, that was a good process. I'll go back to my screen. What's this?
Okay, this would be 63 divided by 7. 9 times 7. So 9x to the 6.
Good. So it sounds like you did this. So I know you didn't write out every single step, but I think this was your thought process?
Yep.
Okay. Now, is there any other way to simplify this expression besides multiplying 9 times 7?
Okay, you can just cross multiply. I mean, yeah. Well, not cross multiply. You can just cancel out the 7s.
And what do you get?
9 over 1, which is just 9.
Which is what you got this way.
Mm-hmm.
Okay, good. And by the way, it's good that you were careful there. You're right. This is not cross multiplying. Cross multiplying is what you do when you have two fractions that are equal to each other. Cross multiplying is what you do when there's two fractions that are equal to each other. So we're not setting these two fractions equal, so we're not cross multiplying. What we call this is diagonal canceling. Diagonal canceling. I think this is a really useful trick here because this comes up so often now at this point. So what's this?
That would be 11.
Because you can just cancel diagonally. Good. What's this?
32.
Okay, good. So that's a very useful arithmetic trick here because that is going to come up so often. Okay, in any case, so that's something we could be using to check our work. In any case, you got this problem correct. That's good. By the way, I would say probably your instructor, when they do this, they might use some little shortcuts. There are shortcuts you can use on these problems. And if you have some shortcuts that work for you, that's okay. But you know, it didn't take that long anyway. So at this point, I don't think there's too much point trying to learn shortcuts. The basic method is pretty straightforward anyway, and it helps us to avoid getting confused. So we don't really need to use any shortcuts. We can just use these basic ideas here of these particular antiderivatives to get to the answer fairly quickly. Okay, good. All right, let's try this problem on your screen. Now this problem is harder than any of the problems that we've done today, and this one I'm not going to demonstrate. I'm going to give you a chance to think about it and try to do it. This is harder than the problems we've done today, but there is a way to solve this using the techniques and concepts that we've talked about today. So give this a shot.
Okay. Okay, so I'm going to start off by rewriting f prime as so the derivative. Okay. Okay.
Let's see. Okay, that looks good. Okay, good. So this is harder than the problems that we did earlier, but you figured out a way to solve that. So that's very good, and it looks like we ended up with the right answer. So now we've made a big leap in the types of functions that we can take antiderivatives of. This looked much more complicated than the little functions we were dealing with before. So the trick was to rewrite it so it was the type of function that you did know how to deal with, a polynomial. Okay, very good. I'll go back to my screen. That's good that we adapted to that problem. Now, basically, it kind of sounds you didn't quite explain what your logic was there. It sounded like you were basically canceling an x out of both of these terms.
Right. I was just
Now, the problem is, how do you know that's legal? Sometimes people cancel when it's not really legal.
Mm-hmm.
So how can we be sure that's legal? Well, I don't want to make you uncertain, so that was correct there. Something that you might have done, though, that might have improved your confidence, how can we rewrite this as two separate fractions?
We can, well, we can rewrite it as 2x to the 5th over x minus x cubed over x. And then on top of each fraction, we can pull out an x, or rewrite it as x times 2x to the 4th over x minus x times x squared over x, and then that shows you that you can cancel the top and the bottom x's.
Good. That sounds like you're on the right track. That would be even more step by step than I think is necessary, but that's good. The key thing is, I think if you rewrite it as two separate fractions, now it's clear you can cancel, is the point. So maybe to make it a little bit clearer, you could rewrite it like this. Now that should be good enough, because how do you divide two numbers with the same base?
Divide two numbers with the same base, you subtract the exponent.
Good. What's the exponent on this x?
1.
Right. So when you subtract the exponents, what do you get here?
X to the 4th.
And here?
X squared.
Okay, good. All right, so that just confirms that you did that correctly. All right, now I'm not saying you have to write it this way every time. The way you did it is fine. If you're confident in your algebra, you can write it just the way you did. If you're confident, you can write it just the way you did. But I know there have been times in the past when we weren't quite sure whether we could cancel or not, or we thought we could cancel and we couldn't. And as we've talked about, the way to build your confidence when you're not sure is to make smaller little baby steps. So if you weren't sure whether you could cancel, you should try to rewrite the expression as separate fractions. And then those separate fractions will show you where you can cancel and where you can't. So like I'm saying, the way you wrote it is fine. You don't have to write it this way, but you should know in your mind that you could write it this way. Okay. Good. All right, so and that was the point. That was the point of this algebra that we went over here. The point of this algebra was to show us how we can rewrite one fraction as three separate fractions when that's helpful to us. All right. And again, it's good to remember, how do you divide two numbers with the same base?
You subtract the exponents.
Okay, excellent. Let's try this on your screen.
Okay, cool. Yeah, that's good.
Okay, very good. Excellent. Okay, that's good. That was a good, careful approach. And it's good that you remembered to put in the plus c. After doing all that work, it would be easy to forget that plus c at the end. So that's good that you put that in there. What's the relationship here between f and f prime? How would you describe their relationship in words?
F and f prime. Let's see. F of x is the antiderivative of f prime of x, and
Excellent.
f prime of x is the derivative of f of x.
Excellent. Very good. They are. That's right. Very good. I'll go back to my screen. Good. All right. That's some good that's a good progress on that type of problem.
Okay.
Let's see. Okay, let's try this.
Okay, g prime of y equals y cubed. So g of y is just 1/4 y to the fourth plus c.
Okay, excellent. So I tried to confuse you here by changing the letters, but you saw that that didn't make much difference. What is y in this problem?
Y is a variable.
Good. And what's g?
G is the function.
G is a function. Good.
Mm-hmm.
And what's c?
C is a constant.
So notice there's three different things that letters can stand for. Letters can be variables, functions, or constants. Now you're used to seeing x used as the variable and f used as the function, but there might be some problems where there's a different variable, a different letter as the variable and a different letter as the function, but you can still apply the same approach. So in our table here, I'm using x for the variable, but the variable doesn't have to be x. It could be any letter. Okay, good. Good.
Cool.
Okay, here's a problem that's different from the ones we did before, maybe harder than the ones that we did before, so we haven't talked about this directly. Maybe we'll take a few seconds to see if we can figure this out. So can you figure out what this is?
It's the natural log of x plus c.
How do you know?
Because if you take the derivative of natural log of x plus c, you get 1/x.
Excellent. Terrific. Excellent. Good. So how could you figure that out? Well, you just have to ask yourself, what's the function whose derivative is 1/x? What's the function whose, well, what is the function whose derivative is 1/x?
The natural log of x.
Excellent. Good. All right. Why did you put in the plus c? Well, you put in the plus c because we're trying to write the most general antiderivative here, right? But since we're trying to write the most general antiderivative here, we're actually missing something. Remember something new we learned today? That the derivative of this function is also 1/x. So here's something new. If we're going to write the most general antiderivative now, we have to include these absolute value signs.
Okay.
Now, we haven't proven that the derivative of this is 1/x, but we never proved that the derivative of ln x was 1/x either. We're just taking it on faith. It's the proofs in the textbook. But anyway, we saw today that this also has a derivative of 1/x. So this is a little bit trickier than the ones we did before. Now we have to remember not just to put in the c, we also have to remember the absolute value signs. Your instructor does do that in their answers. Your instructor does put the absolute value signs in their answers, so I think we'll need that for full credit on those problems. Okay, so that's one thing that we'll have to watch out for here. Okay.
Okay.
Let's try this problem.
Okay, so f prime of x equals 3 times 1/x, which we can just simplify as, well, okay. The antiderivative would be 3x times the natural log of absolute value of x plus c. Okay.
Okay, like this?
Yep.
Okay. This one we had a little trouble with, so let's talk about this again. So how did you handle this 3 here? I think what you did with the 3 is you took its antiderivative, right? You said the antiderivative of 3 is 3x.
Right.
But that actually is not the correct method when you have a constant multiplied times another function. When you have a constant multiplied by another function, you don't take the antiderivative of the constant. If you have a constant multiplied by another function, you don't take the antiderivative of the constant. For example, let's look at this example here. We had 2 times x cubed.
Mm-hmm.
You didn't take the antiderivative of 2.
Right.
In this case. Or maybe this is a better example here. I had 7 times x to the 4th. Well, I didn't take the antiderivative of the 7. I didn't write down a 7x here.
Right.
I just copied down the 7. So when a constant is being multiplied times another function, the constant multiple rule does not tell you to take the antiderivative of the constant. Instead, it says just pull the constant out of the antiderivative, take the antiderivative of the remaining function, and just multiply it times the constant. I can see how you can get a little confused here because I've never kind of written down the constant multiple rule kind of technically in math. I think maybe it's a little bit easier. Maybe I'm wrong, but it's a little bit easier just to see it with these examples. So when we're using with the constant multiple rule does not tell us to take the antiderivative of the constant. We just pull the constant out. Notice here we didn't write down a 7x. We just multiplied by the 7. Okay, so going back to the example we were just working on here.
Okay.
So instead I'll demonstrate this. Oops. So what we should have done here is we should have said we have a constant multiplied by a function. So I'll just copy the constant down here. And now I'll just take the antiderivative of the function. So what's the antiderivative of this function?
The natural log of absolute value of x.
And then we remember the plus c.
Mm-hmm.
Okay, so that's the method here. So that's the constant multiple rule for antiderivatives. When a constant is multiplied by a function, you don't take the antiderivative of the constant, you just recopy the constant. And then you take the antiderivative of the function it was being multiplied by. All right, so then that would give us this instead. So just to review that again, here was the process. We see that we have a constant multiplied by a function. So we don't take the antiderivative of the constant, we just copy the constant. And then we take the antiderivative of this function, and that was natural log absolute value x. Okay, very good. All right, so that would be the process for that. Okay, good.
Cool.
Okay, let's try this problem.
Okay, so the antiderivative of f times 1 over x is, 5 times 1 over x is 5 times the natural log of the absolute value of x plus c.
How would you check that?
You could take the derivative of natural log of x and then the derivative of c, and you would just get 1 over x.
Well, we have to take the derivative of 5 times the natural log of x plus c. What is this?
1 over x.
Well, then we if that was the case, we would have gotten it wrong because the function wasn't 1 over x.
5 times 1 over x.
All right, looks like we're having a little trouble with that one. So what's the process for taking that derivative? Well, first we would use the sum rule. The sum rule for derivatives. What's the derivative of c? 0. Now, how do you take this derivative?
You pull the 5 out.
That's the constant multiple rule for derivatives. Do we take the derivative of the 5?
No.
No, we don't take the derivative of the 5. And then we would get this. Okay, and then that confirms that we really did get back to where we started. So that showed that we actually did do that correctly. Okay. What is this?
It's 8 times 1 over x.
And what's this?
1 over x plus c. Wait, no, that's antiderivative. It's just 1 over x.
So notice the difference between how you treat a constant that's being added and a constant that's being multiplied. Did we take the derivative of this 8?
Yep.
Good. Did we take the derivative of this 8?
No.
No. So there's a big difference between constants that are added and constants that are multiplied. When a constant is multiplied, you don't take the derivative of the constant. But when a constant is added, you do take the derivative of the constant. Okay, good. Okay, all right, so what's f of x here?
F of x here is 8 times the natural log of the absolute value of x plus c.
Okay, good. Now try this example.
Okay. This would just be, let's see, 8x plus the natural log of the absolute value of x plus c.
Okay, excellent. So now we have a nice, beautiful point being made here. So in this case, did we take the antiderivative of the 8?
Yep.
The antiderivative of 8 is 8x. In this case, did we take the antiderivative of 8?
No.
No. So this is the point I wanted to make here. This is what you might get confused between. You don't want to confuse the sum rule and the constant multiple rule. When a constant is being added to something, you do take the antiderivative of the constant. But when a constant is being multiplied times something, you don't take the antiderivative of the constant. Okay, let's try this.
Okay, so f prime of x equals 9 times 1 over x. So f of x equals 9 times the natural log of the absolute value of x plus c.
Okay, excellent. It's good that you remembered the plus c, and it's good that you remembered the absolute values, and we did not take the antiderivative of the 9, because we're using the constant multiple rule for antidifferentiation. Very good. Let's try this one.
Okay, so f prime of x equals 5 over x. So f of x would be equal to, f of x would be equal to, let's see, the natural log of the absolute value of x times 5 plus c.
Okay, got an answer? What's your answer?
The natural log of the absolute value of x times 5 plus c.
Now, did you mean this? Or did you mean this?
The bottom one.
Okay, excellent. Good. I just wanted to make sure that was clear. Good.
Mm-hmm.
So in order to make that clearer, it might be better to write it like this in your final answer.
Okay.
Because otherwise, when you write it like this, it's a little bit unclear whether we're taking... So are we taking the log of the 5?
No, we're not.
But if you write it like this, it's a little bit unclear what you mean. So it might be good to write the final answer like this. Now, how did you come up with that? Well, how could I rewrite this? So we know how to take the antiderivative of 1 over x. How could I rewrite this so it has a 1 over x in it?
You can rewrite it as 1 over x times 5.
That's right. Or then, to make it more similar to what we've worked on before, 5 times 1 over x. And then you can get straight to this answer here. So this problem is pretty much identical to the ones that we were doing before, if you recognize that 5 over x is the same as 5 times 1 over x. Okay, good. So you got the, looks like you got the right answer there, so that's good. Let's try this one.
Okay. So we can rewrite the f prime as -1 times 1 over x. So f of x is just negative natural log of the absolute value of x plus c.
Check that.
Derivative natural log of x is 1 over x, -1 over x. Okay, yeah, I think that's good.
Okay, excellent, good. So I just wanted to make sure we could handle that negative sign there. Okay, all right, so now I think we're ready to add to our list of particular antiderivatives. So the function that we were just dealing with here is 1 over x. And what's its antiderivative? What's its particular antiderivative for this table?
The natural log of the absolute value of x.
Good. It's good that you remember those absolute value signs. Good. We're not writing in the plus c because the table is just doing one particular antiderivative. Now notice in the table I only wrote 1 over x. But we can also handle things like 5 over x by just rewriting it like this. So knowing how to deal with 1 over x also helps you to deal with a lot of related things that you can re-express as a 1 over x. Good. All right, try this one on your screen.
Okay. Okay, so this was 8x. This was 5. Derivative of 8x is 8. Derivative of 1/5 x to the fifth is 5/5 x to the fourth. 1x. Derivative of natural log of x is 1/x plus c, 0. Okay, cool. Yeah, that's good.
Excellent. That's good that you double checked yourself. Okay, so notice now we've combined together a whole bunch of different ideas. So we've definitely ramped up the difficulty here. Now we can do much more complicated types of expressions, but we're still able to find that antiderivative. Okay, very good. All right, that's right. That's a good integration of a bunch of the different things we talked about. I'll go back to my screen. Let me say one more thing here. What's the answer here?
Let's see. F prime of x equals 1/x. So f of x is the natural log of the absolute value of x plus c.
Good. That's the right way to do this. Now, let's also look at a way that doesn't work. Here's a way that doesn't work. The other thing you might have tried to do here is, how can you rewrite this so it's not a fraction?
Okay.
How can we rewrite this so it's not a fraction? Now, this is going to actually turn out not to work in this case, but we can learn something interesting. So how could you rewrite this so it's not a fraction?
X to the -1.
Now, this might seem like a brilliant idea because now it's a power function. And we should be able to use antiderivatives for power functions. We haven't done with negative numbers. Do you remember what would be the rules here? What should we do to the exponent? Increase it or decrease it to find the antiderivative?
We should increase it by 1, which would just be 0.
That's okay, no problem with that. And then remember that when we're doing antiderivatives, what number would go down here?
Well, 0.
Because these numbers match.
Mm-hmm.
Well, do you see the problem?
Yep.
What's the problem?
1 divided by 0 doesn't work.
Yeah, that's undefined. So I just wanted to point out this is a method that would not work. That's why, so this is 1/x is a special function with a special antiderivative, natural log of x. If you try to apply the power rule here, you hit a dead end. So the power rule does not work in this case. So why did I even bother mentioning it if it doesn't work? Well, it would work on many similar cases. For example, how would you find this antiderivative? Well, how could you rewrite this so that it's not a fraction?
X to the -2.
Now, to take the antiderivative, what should be the new exponent here?
So you add 1, so it's x to the -1.
Excellent. You add 1 to find the antiderivative, and what goes down here?
-1.
Well, that's perfectly fine. That's defined. So normally this is a good trick. Normally it's a good trick when you have 1/x in the denominator to rewrite it with a negative exponent. So normally that trick works. It just doesn't work for x to the -1 power. It doesn't work for x to the -1 power because if you try to apply the power rule there, you have to divide by 0. Okay, so in this one particular case, it doesn't work. But I think that's still worth mentioning because this is a type of antiderivative you'll probably have to take eventually, antiderivatives like this. So this is generally a good trick to rewrite something as a negative exponent. It just doesn't happen to work for 1/x. Okay, I'm not going to talk about that too much right now because this particular section that we're working on in the textbook doesn't deal with this function yet. But it was worth mentioning this because you will be getting to these functions pretty soon in a couple sections later. I think I'll erase that right now for the time being since we're not focusing on that yet. But
Okay.
that is an idea that'll be important later. All right, so normally it would be an excellent idea to re-express this as x to a negative exponent. But we just saw that trick doesn't work for 1/x. For that, you need a special antiderivative. We just went over that. Okay. Okay, here's a new one. We haven't talked about this before. See if you can work out what f of x would be here.
Okay, so f prime of x equals cosine of x. So f prime of x is, well, what gave us cosine of x? What gave, that would be sine of x. So f of x equals sine of x.
Okay, done?
Yep.
Okay, very good. We have to remember the plus c. And how would you check that?
We can take the derivative of sine of x.
And what do you get?
Cosine of x.
So did it work?
Yep.
Outstanding. Excellent. So good. That was a good job. So you have to ask yourself, what's the function whose derivative is cosine x? What's the function whose derivative is cosine x? Well, that is sine x. Good. So that came out correctly. Okay, very good. So try this problem.
Okay, so f prime of x equals 5 times the cosine of x. So what gave us cosine of x? That would be sine of x. So f of x equals 5 times the sine of x plus c.
Okay, good. So I think we have now another particular function and its antiderivative. So the function we were dealing with here is cosine x. And what's the particular antiderivative I should write here?
Sine of x.
Good. And then once we have that memorized, we won't have to work it out by trial and error each time. So what's the antiderivative of cosine x?
Sine of x.
Good.
Three sine of x plus c.
Try this one on your screen.
So f of x equals negative 8 cosine of x. Derivative of sine of x gives us cosine of x. Constant mode. Okay.
Okay, good. That's good. Good process. I'll go back to my screen. So the way I would think about that is I would say I've got a constant multiple here. So I just copy the constant multiple, and then I just take the antiderivative of the function. And then we get the answer that you got. Very good. Okay, let's try this.
Okay. So f prime of x equals sine of x plus c. What gives us the sine of x? Derivative of cosine of negative x. So negative cosine. X plus. Oh, okay. The derivative has c in it, so this is. Yeah. Okay, cool.
Okay. I unintentionally made that kind of a trick question. So I was warning you earlier about not confusing taking derivatives and antiderivatives, and now I keep making that same mistake in this session. So I'm illustrating my warning by falling into my own trap here. So I didn't intend to put the plus c in the f prime, but that's good that you noticed it there. But as long as it's there, now you need to add another constant.
Sure.
So you'd have to call it plus d. Okay, so that was an unintended difficult problem. I didn't really intend for it to be like that. Okay, but you did handle it right by putting in the plus cx, but then we need a new constant for that. Okay, all right, that's good that you noticed that. That was kind of unintentional though, so let's erase those. Let's erase the plus c and the plus cx and the plus d. I didn't mean to get into that. So try again. The function was supposed to be f prime of x equals sine of x. F prime of x equals sine of x, so what's the answer now?
Like that.
Excellent. Okay, very good. Okay, that was, and so you figured this out correctly. That's good that you were careful to figure out the signs. What's the derivative? What's the derivative of cosine x?
The derivative of cosine x is negative sine of x.
Right. So the derivative of negative cosine x is
Sine of x.
There you go. It's a little bit tricky, but you thought it through and you got it correct. Okay, great. That's good. All right, so you got that correct, even though it was an unintentional trick question. Good. I'll go back to my screen here. All right, very good. Well, I think then you were already ready to go back to our table and add that. So now we've figured out a new antiderivative, the antiderivative of sine x. What's the antiderivative of sine x?
The antiderivative of sine x is negative cosine of x.
Okay. Now, you figured that out with a little trial and error, but it might be just as well just to memorize this as well, so you don't have to figure it out every time, or maybe you can kind of do a blend of figuring it out and memorizing it. All right, so that would give us this. Okay, good. So I think this could easily be confusing here because, oops, uh-oh.
Are you slamming your mouse down?
Yep.
Yeah.
See? That's the way to do it. All right. So here's the thing that I think it could be confusing. What's this?
Derivative of sine of x is cosine of x.
And what's this?
Negative sine of x.
And what's this?
Okay. So the antiderivative of cosine of x would be, so what gives us cosine of x? Sine of x.
And what's this?
What give, negative cosine of x.
Okay, very good. So here's what I think is confusing. When you take the derivative of the sine, does the plus or minus change? When you take the derivative of the sine, do you put in a negative?
Nope.
When you take the antiderivative of the sine, do you put in a negative?
It does.
So that's what I think could be confusing. We don't want to confuse the derivative and antiderivative. You take the derivative of the sine, you don't need a negative sign. But if you take the antiderivative of the sine, you do need a negative sign. When you take the derivative of cosine, do you need a minus sign?
You do.
But when you take the antiderivative of cosine, do you need a minus sign?
Nope.
Okay. Well, I think that's clear. It just means you just have to take your time and double check yourself. If you take your time and double check, you can avoid those mistakes. So it's hard, but not super hard. Okay, good. Let's try this on your screen.
Okay, so this would just be 3 sine, I'll give you sine of x. Okay.
Okay, excellent. Good. How could you re-express that?
Yeah, like that.
Okay, good. Your instructor doesn't necessarily require you to simplify, but I think that's a simplification we should get into the habit of making. Okay, good. All right, so we ended up with a correct answer there. And you could always check that by taking the derivative, and you would see that you got back to what you started. Okay, excellent. That was good. All right, let's try this one on your screen.
Okay, so it gives us cosine of x, just sine of x. Okay.
Perfect. Excellent. Very good. I'll go back to my screen. That's right. Let's try this example. So we're trying to find f, as usual.
Okay. Okay, so what gives us a sine of x? That would be, okay, this one's easy. Okay.
Okay, excellent. Good. There's a couple different ways you can think through this. But I think the method that you used, that seemed to work good for you. Okay, excellent. Good. So that came out correctly. Good. I'll go back to my screen. Let's try this.
Okay, so what gives us cosine of x? That's sine of x, and then we need negative. So we need negative. Okay.
Perfect. Excellent. Very good. All right, back to my screen. Let's try this problem.
Okay, so it gives us 1. It'll just be x. Gives us sine of x. Gives us sine of x. That would be negative cosine. Yeah, negative cosine. So just plus. What gives us this? 4. So the derivative of x is 1. Derivative of cosine is negative sine of x. This, we use our rule. Well, to take the derivative, 4 over 2 is 2. 4 minus 1 is 3. 2x cubed plus c. Okay, cool.
Good. Looks like you were very careful there. That was a good, careful approach. The most important thing is to be careful with the plus and minus signs when you're dealing with sine and cosine. And it looks like you were very careful with that. So that's good. Okay, good. So that integrates a bunch of different rules together that we've talked about. That was an excellent process. Let's talk about that last term here. There's 2 different ways to do this term. I'm not quite sure which way you did. So one way you could do is you could just say, what's the function whose derivative is 2x cubed? And you might say, well, I know this has to be a 4. 4 times what is 2? 4 times what is 2? Well, 4 times... No.
Oh, yeah, 4 times 1.
4 times 1/2 is 2.
Gotcha.
All right. Well, okay. I thought this was the method you used, but maybe it wasn't. Maybe you didn't do it this way. I thought this is what you're doing because it sounded like you were saying whose derivative is 2x cubed. Okay, that's one way to do it. That's probably not the best, most reliable way. I think the most reliable way, that's just consistent with what we did before, is to say, first I'll use the constant multiple rule and just bring down the 2. And then what's the antiderivative of x cubed?
1/4 x to the 4th.
How do you know? Well, you could have figured it out by trial and error, but you could have just memorized that pattern. Remember, we saw the pattern is increase the exponent by 1, and then the coefficient is 1 over 4. Maybe this is the method you used. And okay. So there's 2 different ways to think about that. I think the more mechanical way is probably safer. We're less likely to make mistakes this way. Okay. So maybe, all right, I thought you had done it the other way, but you're actually doing it this way. Okay, so anyway, it sounds like you used a good approach, and you got the correct answer there. All right, good. Good. Okay, well, here's a new one. We haven't talked about this before.
Okay. That's just going to be e to the x plus c.
Excellent. Good, because what's the derivative of e to the x?
It's e to the x.
Great, and what's the derivative of c?
0.
Okay, excellent. So this one was not one of the hardest that we've gone over. Very good. Remember, this is what's called the natural exponential function. Of course, we would not use our power rule here. Why does the power rule for antiderivatives not apply?
Because to use the power rule, we need to have, well, for one, it's a different power rule, and then also you need the variable on the bottom and the constant on the top.
Yeah, we do have a power rule for antiderivatives. There is a power rule for antiderivatives, but it doesn't apply here because this is not a power function. It has a constant on the bottom and a variable on the top, but power functions have a variable on the bottom and a constant on the top. So we just need a different rule. We need the rule for natural exponential functions. That's it. Okay, well, that was not a very complicated function, so we can go add that to our list here. What's the specific antiderivative of e to the x?
E to the x.
And what's the derivative of e to the x?
E to the x.
And what's the antiderivative of e to the x?
E to the x.
That was fun. Okay, good. Very good. So what's the only function which is its own derivative?
E to the x.
Right, or a constant times e to the x. Good. And what's the only function who's its own antiderivative?
E to the x, or
or a constant times e to the x.
Yeah.
Or to be more specific, it's one. E to the x is one particular antiderivative of e to the x. Okay, good. All right, excellent. try this.
Okay, so this is just 3e to the x plus c.
Okay, that was a close one. Okay, excellent. Good. So technically what we're doing here is we're doing the constant multiple rule. First you would say, just bring down the constant, and then what's the antiderivative of e to the x?
Itself, e to the x.
Good. Okay, good. Let's try this one.
Okay, f prime of x equals negative e to the x. So f of x, the antiderivative is negative e to the x plus c.
Like this?
Mm-hmm.
Good. Excellent. So the way I would think about this technically, I would say this is really negative 1 times e to the x. So then I can use the constant multiple rule, bring down the negative. The antiderivative of e to the x is e to the x. And then we can simplify. I'm not saying you have to write out all those steps, but it's good to know in our head that that's what we're doing. Okay, very good. Let's try this one on your screen.
Okay, so antiderivative of this is just negative. What gives us cosine of x? Sine of x. Gives us cosine of x. Sine of x. Okay, so negative x to the fourth derivative of sine of x is derivative of sine of x is cosine of x. Okay, cool.
Okay, excellent, good. That was a good, careful process. It's good that you're paying attention to details and double checking for mistakes, especially with the plus and minus signs. It's especially easy to make mistakes with the plus and minus signs, but you were very careful about that. Okay, that's good. Okay, so I'll go back to my screen. Okay, so those what we've been working on now is section 4.9. Those are all the antiderivatives that we need for section 4.9. Later, as we go on, we'll have to learn other antiderivatives, but those are the only antiderivatives that we need for section 4.9. There's a little bit more to cover in 4.9. There's some harder problems that we need to talk about, but those are the antiderivatives. But let's summarize what we've seen here so far. So you're not allowed to bring notes to the test, right?
Nope.
Now, I noticed you sent me a table of anti-differentiation formulas, and you can see that we've been kind of going over a lot of the stuff in that. But you're not going to be allowed to use that table during the test, or are you?
No.
No. Okay. So we need to memorize those ideas. Although a lot of them they only have to be semi-memorized, because if you forget them, you can kind of figure them out again. So we have particular So without looking at your notes, can you remember one of the functions that we've learned? So we didn't go over everything in that table. We only went over the parts of the table that we needed for section 4.9. So can you remember one of the functions we went over? What's one of the functions we went over today that we learned how to take the antiderivative?
X to the n.
Excellent. Good. A power function. And what would that give us?
That would give us 1 over n plus 1 times x raised to the n plus 1.
Okay, good. Notice this is not the power rule for derivatives. This is the power rule for antiderivatives. It's important not to get those confused. Excellent. We won't write the plus c here because these are particular antiderivatives to be consistent with the table your instructor gave you. Okay, can you remember from memory another function we talked about today that we know how to find the antiderivative of?
Yep, we talked about if the function is just a constant. So if the function's k, I think we used the letter k, and the antiderivative of that would just be kx.
Excellent. So that's the constant rule for antiderivatives. Excellent. Okay, what else?
We just talked about e to the x, and that's itself all the time. So e to the x.
So this was a power function, but this is the natural exponential function. The difference is that here we have a variable raised to a constant, but here we had a constant raised to a variable. Good.
Then we also talked about the function is 1 over x. Then the antiderivative is the natural log of the absolute value of x.
Yeah, that was something new. We saw how we could put in these absolute values. So it's good that you're remembering that. And we saw this is the one case where we can't use the power rule. It won't help you to write this as x to the negative 1 and then say the antiderivative is 1 over 0, x to the 0, because that would be undefined. What if you had, say, 1 over x cubed? Well, then you could just write that as x to the negative 3, and you could apply the power rule here. We didn't talk about that today because it was not in section 4.9, but it will be something you'll need later on, so that's still worth mentioning. Okay, good.
Okay. And we also talked about some trig identities. We talked about if the function is cosine of x, then the antiderivative of cosine of x would be sine of x. And then if the function is negative cosine of x, then the antiderivative would be negative sine of x.
Good, that's right. Now, that's something you can kind of figure out from the previous line, so I'm not going to include that in the table. That's true, that's good. But since you could kind of figure it out from the previous line, I won't write that down separately.
Okay, okay, that's right. I was thinking of a negative sine of x gives us, actually, that one we didn't talk about either. We're just going to infer that one. So sine of x is, the antiderivative of sine of x is negative cosine of x.
Good. And as I think you were just noticing, that would easily allow you to figure out the antiderivative of negative sine x as well. Okay, anything else?
I think that's all we talked about. I might be forgetting something.
I think so too. Let's see. Now, we also talked about some other rules that are in the table. We talked about the sum rule for antiderivatives. We talked about the difference rule for antiderivatives. And we talked about the constant multiple rule for antiderivatives. Those are all in the table your instructor gave you. But I think for us, it's easier just to treat those as like rules rather than actually putting them directly into the table. So here's the specific things that we went over in this table. So obviously, you want to have this well memorized. Or like I say, in a way, it doesn't quite have to be memorized because you can kind of figure it out if you forget it. But these are things we have to be comfortable with anyway. And as we go along, so basically this one of the main jobs in this chapter is learning how to take harder and harder antiderivatives. So these are the easiest antiderivatives. As we go on, we're going to be trying to find harder and harder antiderivatives. It's kind of like what we did earlier. Do you remember how I've been telling you that half of calculus is about finding derivatives? Mm-hmm. Well, this is the other half, kind of. The other half is about antiderivatives. There's another name for that as we go along, but the other half is basically about antiderivatives. So remember that what we did earlier in the course is we learned how to take derivatives of more and more complicated functions. So that's kind of what we're going to do in this chapter. One of the things you'll do in this chapter is find the antiderivatives of more and more complicated functions. That means we have to be super good at this material. This material, all these problems we did today have to be super easy for us, because pretty soon we're going to be doing problems that are much more complicated than this, and this will just be one step. So just like we had to get to the point where the chain rule and the product rule and the power rule were all really easy for us to do really complicated problems, we have to be at the point where these ideas are very easy for us. And I think we were pretty much kind of already there. I think we were doing real good on those today. So the key is just to practice, so that we keep those things in mind. Okay, so there are still some other types of problems to see how to do in section 4.9, but I think we made good progress on that for today.